Right, let's begin the Python session for the simple linear regression. Uh, so we will be looking at what we discussed in the theoretical session. We'll just look at the Python point of view. So this will be a short video. So I have a data set like in my data folder. There's one data set called salary data, wherein we have two features. One is the years of experience and the salary. Okay, and obviously the task is that by looking at the years of experience, can I go and predict what the salary could be, right? So let's go and start looking at the code. I have the code ready just to save some time. I'll be discussing about for each line what we're doing. So I just imported the pandas library and numpy for now, and I took the data into my pandas data frame, and this is how the data frame looks like. Okay, we have years of experience and salary. You can notice the years of experience is a float column, and salary is a continuous column. Okay, and if you just want to go and look at a TF dot summary, so this will show. Sorry, it should be df dot describe. My bad. Stop that. So when I go and do df.describe, it will show how the distribution looks like. So the maximum number of years of experience that we have in the data set is close to 10.5, and the minimum is 1.1. You can notice the 50 percentile is almost at the center. It is not exactly at center, but almost at center, like 4.7. And similarly, we have some distribution in salary. We'll look at how the distribution is like for now. And if I look at the top 5 records, this is the top 5 records. And if you want to look at the unique salary, we have 30 unique salaries. Okay, I've already run this. And before I move forward, this is a supervised learning because we have the target variable, which is salary, and one independent feature, which is the years of experience. And as you know, the number of years of experience is an independent. It will be having an effect on salary, but the other way around is not true. Okay, at least for this data set, the other way around is not true. Of course, in today's world, the dimensions would have changed, and the salaries and years of experience would have a various effect because of COVID and all. But anyway, let's move forward. Just for plotting purpose, I'll be importing the matplotlib and cpon, and I just want to look at how the distribution of the target variable is like. So this is how the distribution looks like. It has a couple of outlets. Of course, the minimum data set is around 40,000 and the max is around 1,20,000. And you can see the mean is not in the center, it's somewhat below. Of course, we don't have to treat the outlets for now. It's we are just building a simple model, so don't worry about handling the outlets for now. And I also can divide the salary in bins and see how the occurrence is there. So maximum data is present between 60,000 to 70,000 and a little around 80,000. So at the center, it is very less. But there's a lot of people who are having 60,000 salary and a lot of people who are having like 1,20,000 salary and so on. And if you want to look at the distribution, this is how this plot looks like. It's not perfectly uniform normal, but we can just run the show with that. And if you notice the plot between the years of experience and salary, we have some kind of a linear relationship. Okay. Of course, it is not exactly linear, but we can deal with it. There are a couple of odd records which are far away, like in this case, and like in this case. But that's okay. So we will try to come up with some model which can explain the variance that is present here, and we'll continue. Okay, and then I just want to check the correlation between my target and my dependent feature. So years of experience is my independent one with it is having 97% correlation with my salary. Because we have like only two features, we don't have to look at the second record. As I said in the previous records, this feature what we see, we can ignore it. Years of experience will have high correlation with years of experience. We have to just check with the effect of salary and years of experience. Like with with 1 unit change in years of experience, what is the change in salary? So you can notice that there is like 0.97, which is very close to 1. So it is very high correlating features. And if you remember our session with list, how to slice list is by using this colon symbol, wherein when I say colon 4, it will take the first 4 attributes. And when I say colon 4 colon, then it will take only the last attribute. Similarly, we can do the same operation in pandas. So instead of using directly the slicing operator, here we will use a slicing operator using .iloc. So what the .iloc would be doing is I'm going to choose all the records, but I will take only first column. Okay. And similarly for Y, I'll take only the last column and all the records. So when I do that, I will have the shape. You can notice the shape 30 records in my independent feature and 30 records in my dependent feature. We have only two features. That is why your shape is only one in the column field. And if you notice, the type for X is pandas data frame. Okay. And now what we'll be doing is we'll be randomly splitting the data set into 80% and 20%. 20% will be left for our validation purpose, and 80% will be there in the training data set. And if you notice the total records, we had 30. So after doing the split, we have like 24 records in train and 6 records in our validation. Similarly, for Y train and Y test, it would be 24 records in Y train and 6 records in our Y validation. Now, what we'll be doing is we'll be using the ordinary least squares model, which is present in stats models library, and we'll be fitting on our X and Y. Why we are using stats model is like it can help you see all those probability scores like the p value and the f value and all, so that we can just have a significance if we can just notice this details like what is the adjusted r square and for a given independent feature what is the p value. So you can notice the adjusted r square is around 97%, which is very good for the model. And the years of experience is having a coefficient of 1.34 to the power of 4, and the p value is quite less than 0.05. It is highly significant. And similarly, the f statistic is also highly significant. So if you look at the f statistic, it is less than 0.05. E to the power of minus 19 is like 19 zeros, and then followed by 1.18. Okay, so this model is significant. Our beta is also significant. That is how we get all the details. So because both the features are significant, then we can say that we can use this model for prediction purpose. Now, we also discussed a couple of scenarios wherein we had 4 assumptions to make, right? So we just look at, let us look at those 4 assumptions, if those 4 assumptions are being followed or not. So the first assumption was that there should be a linear relationship. Of course, we have a linear relationship. It is not exactly linear, but almost linear, I would say. So we have a linear relationship. And I said the error term should be pretty much random. So you do not have any pattern here. It is pretty much random. There are a couple of outliers, however, like these are outliers. That it is not completely homoscedastic. I would say that we would have to treat the data some more before applying the linear model. Only then we can have a better performance. But for now, I'm not doing any fine tuning of pre-processing. We can deal with that later, but I just wanted to show you that the data here is kind of outliers to us, and because of this the model might not might have a lot of variance in the predictions. And you can also see that the QQ plot is almost normal. It's like the residual plots, you have a straight line here. and also the partial regression plot, we also have a straight line here. Okay, we had one more thing like homoscedastic. This is kind of not very homoscedastic, but we can say that if you treat the remove the outlets, probably it would become a homoscedastic. And the quartile-quartile plot should also see some kind of a straight line. Of course, this is not a quartile-quartile plot, but we can also see the quartile-quartile plot. Probably I don't have the code for that now. And okay, this is by using ordinary least squares. We can also use scikit-learn, the sklearn model, and by using linear regression, we can achieve the same thing. But the output which we see in the ordinary least squares from stats model and the output from the linear model are not same. So the linear model will not show all those effects what we saw in the stats model. However, you can see, this is what the predictions and the actual data set looks like. And I have the intercept. My intercept, the coefficients is 9,541, and my intercept is 25,000, and so on. If you want to get the R score, you can get the R score. So in this case, the R score is 93.5. Using stats model, how much we got? Using stats model, also we got. Okay, the stats model was much better. It was 97, but the linear regression was having 93 kind of. Just keep in mind that I did not do any pre-processing. I had to convert the I have to convert the independent features. I have to standard scale at them, but I did not do because this data set is quite less, like only 30 records, and the maximum value is around 10. So it's okay even if we do not do it. Okay. So that is it for a simple linear regression. Probably in the next session, I'll tell you about much more complicated data wherein we have more number of features, and then we'll build a linear model on top of it. Okay, thank you.